Hello, everyone. Thank you for joining us and be welcome to today's webinar, Feed-Forward Fundamentals, Knowing When and How to Apply Feed-Forward Control. I'm Vera from Control Station. I work in the marketing department, and I will be hosting this webinar with Bob from Control Station and George from Sage Feedback. And before we start, I just want to let you know that you are free to input your questions and comments anytime you want here on the GoToWebinar panel. There is a tab named Questions. And in the end of this webinar, Bob and George will be answering these questions. Our presenters are Bob Rice, who has over 20 years of engineering and product management experience in process industry. He is a thought leader and oversees the development of Control Station's award-winning suite of process diagnostic and optimizations technologies, including Plant ESP control loop performance monitoring solutions. And George Buckby is the president of Sage Feedback. He's a leader in the process control industry, focusing his career on enhancing plant operations and advancing control systems. Control Station has been driving innovation in process control since the 80s, and today we support manufacturers around the world, working with leading companies across the process industries. Our focus is improving PID performance, reducing variability, and helping engineering teams achieve sustainable, measurable control improvements. Sage Feedback is a recognized authority in controls founded by George Buckby in 2021, has more than 40 years of experience in process control and optimization, and their objective is to gain maximum value from existing controls.
Excellent. Thanks so much, Vera, for the introductions. What I want to do is just go kind of briefly through this agenda. And I tell you, me and George have our work cut out for us to fit this topic into the 45 minutes. And so you're going to see both of us trying to reel us back in from time to time. But we're going to be covering the fundamentals of feed-forward control, trying to understand the difference between feedback and feed-forward control, talk a little bit about identifying good candidates for feed-forward control. What applications would feed-forward actually provide some benefit? What are some kind of can and cannot do applications for feed-forward? Feed-forward can't solve every problem that's out there and really should be kind of focused on high-value applications. So we'll talk through some of those applications. And then we're going to spend a little bit of time talking about how to design a feed-forward. What are some of the tasks that you have to do to successfully deploy and manage and upkeep a feed-forward system to make sure that it's actually driving value. And we'll go through kind of a quick case study and a Q&A kind of at the end in the food and beverage space. Go ahead, and Vera, and we're going to start with kind of a survey question just around your experience with feed-forward control, right? And so, you know, what kind of is your experience with it? Have you used it before? Have you never heard of feed-forward control? Which, yeah, this will be a good webinar for you, right? You've studied, but never really used it.
This is a huge topic, right? And you're absolutely right. It's going to take us a lot of speeding up to get through this. So hopefully we'll get some insight here from the audience. It is a pretty good size audience, so I expect we'll have a spread across this range of participants, but might help us focus in a little bit as we go along here if we know where the audience is starting from.
Excellent. I know feed-forward was always one of those tools of the trade that I kind of learned early on, and you know, I don't use it probably nearly as much as I should, but the applications that I have applied it to, it's been really successful, right? But it does really kind of take a special type of application.
Right, for the right application, it can make a real step change in performance, if you will. So definitely. So
excellent.
Where do we stand with
I
the?
can share the results here.
Yeah. Right, so kind of as expected, right, a spread across the whole range here. Of course, you wouldn't be here in this webinar if you didn't want to know more about it. So being either completely unfamiliar or having some maybe academic background in feed forward before might have prompted you to want to be part of this, and or if you've tried and met with some challenges. So that's definitely there, and good to see we've also got several experienced practitioners here on the call. So again, when the time comes for Q&A to answer any of those questions, feel free to chime in with those kind of questions and statements of experience from wherever you happen to be starting on this journey here for feed forward control.
So let's keep going.
Sure, so let's just start with the fundamentals, right? Everybody in here has some experience with feedback control. So as we launch into feed forward control, we'll start first with saying we're not giving up on PID and feedback control. That exists. It's going to continue to exist. It's going to be the basis for most of the things that we do. And even with feed forward control, feedback control will continue to play a role, as you'll see when we show you the architectures and how this might play out and be designed and implemented in your plant. So we're going to continue to build on this basis of feedback control and regular old PID as we have used for years and years and years. You can go to the next there.
Yeah. And so when we talk a little bit about the difference between feed forward and feedback, let's think about what feedback control is, right? It is feeding back information. So you are reacting after deviation or after something happens, right? When your car, it has cruise control, right? It's running along and all of a sudden you get to a hill and it starts to slow down. Once it starts to slow down, then the controller starts to react, right? It's starting because there is a deviation that occurs. That's very different than a feed forward controller. So think about when you drive the car, you're looking at the horizon and you say, hey, look, there's a hill, especially if you're towing things, right? You see a hill coming, you're gonna start accelerating before you get to that hill so you don't have as much disturbance or slowdown due to that hill. And so feedback control waits for the deviation to occur. Feed forward control says, hey, look, I know something is happening. Let's go ahead and start to react to it. And there's a lot of different kind of applications out there, and driving is the one that we tend to use a lot, right, as in process control. And so feed forward looks kind of out and sees that disturbance coming along and prepares the controller. Feedback's always kind of waiting for the deviation to occur, right? Lots of different applications out there for feed forward control, but you can think of it, they really work together with feedback, right? Feed forward is, I'm seeing something come along, I want to go ahead and prepare myself for it. Feedback waits for something to happen before it actually does something, right? And so, George, how would you kind of expand upon that kind of difference between feed forward and feedback, or how do you tie those together?
I think that driving a car when you hit a hill is a fantastic example. I mean, and it shows why you need both feedback and feed forward, because you're driving your car, you're coming up to the bottom of that hill, and just before you start up that hill, you stomp on the gas. Well, you don't then give up on controlling the speed of the car when you're halfway up the hill. You continue to maintain, the speed of the car when you're halfway up the hill, and that's the feedback kicking in. So you see the hill, you stomp on the gas, you speed up a little, so you're not going to really slow down when you start on the hill, and then you're going to kind of come back to trimming the gas pedal to get into the right target speed as you head up the hill. So that's the feedback playing into it, and that analogy plays a pretty good role here in when we look at how feedback and feed forward work together through the rest of this webinar. We'll probably bring that example up again.
Mm-hmm.
Then we go to more of a traditional control diagram. You see on the bottom part of this diagram the regular PID controller we're used to. And what's different here, though, is recognizing that disturbances can come in and affect this process. So we have a regular PID loop around the bottom, but then at the top you see there's some kind of a disturbance. that comes along and hits our process. It could be, you know, reaching a hill as you're driving a car. It could be if you're maintaining the temperature control in your room, somebody opens a window. It could be if you're managing a distillation column, somebody changes the feed to the distillation column. It could be any number of types of disturbances that come along and affect your process. And what's different about feed forward rather than just plain feedback is that we will measure that disturbance. You see the sensor there at the top, measuring the disturbance, and then trying to make some kind of correction. And this is really important, before the process is impacted. That's really the important part. So you measure that there's a hill in front of you and you step on the gas before the car slowed down, right? Or you see that somebody opens a window, so you crank up the heat right away. Well, at least now, because it's winter here, yeah, we turn the heat up because somebody opened the window. I might turn the heat up to try to maintain the room temperature, but I do it before the temperature was affected. And that's the idea behind feed forward and feedback. And we'll see through the rest of this webinar how these blocks that are shown on here, the disturbance model and the feed forward element or the feed forward controller, play out, how we might design those, design the controller, and see how that might help us to maintain good control. So again, this is introducing the fundamental idea. We're taking some action by measuring something and taking some action before the process is impacted.
And if you think about like how operators and so forth kind of interact with and know the process, a lot of operators become human feed forward controllers, right? They know, hey, I've got a disturbance coming along and I know the PID controller's not going to be able to handle it. So I'm going to make some tweaks and adjustments knowing this disturbance is coming along, and I'm going to prepare the controller for it. And so operators themselves can behave a lot like feed forward elements. And if you can codify it, if it's repeatable and all these different things that we're going to talk about later, right, it's better to programize it. But a lot of times operators are kind of, you know, becoming those kind of feed forward attributes. And sometimes that's a good thing, but a lot of times you want to codify it and make it so it's not operator dependent, right? And if we go to the next slide, that actually kind of ties us in really nicely to our next webinar, which is when operators become the controller. And one of the things that we like to try to understand are operator interventions. What are the times the operator is intervening with the process? Are they changing modes, set points, outputs while they're in manual? How are they kind of taking over the control, and how can we track and manage that to make sure we're not solely dependent on the operator running the piece of equipment, right? That we can make sure we can understand when there are tuning issues or process issues or control narrative issues, that, hey, we can take the knowledge that operator has, codify it, so we don't have to depend on, you know, Billy to run the board because he runs it the best, right? And so we're going to have Eric Gilbert, who's the Director of Process Control for Smurfit Westrock, kind of go through one of the KPIs that they use pretty reliably, called operator interventions, to kind of understand how operators interact and what kind of pros and cons there are with operators driving the process versus the DCS. And so that's going to be a great webinar next month with Eric and them.
That's a great idea for a webinar. I mean, loops in manual are rarely the problem. They're usually the symptom of something underlying it that's going wrong. So another great webinar to get some insight into what's happening. All right, so let's start on feed forward. What can a feed forward controller do and not do? Just kind of set some expectations for what this thing can do. Well, what feed forward can do is it can address measured disturbances. If I can see that something's going to happen, I can do something about it. I look outside, I see that it's getting cloudy, I'm going to go for a walk. It might rain, so I'm going to take an umbrella, right? I'm going to do something about it. A measured disturbance. I can see something happening, I can do something about it. It can help in that way to reduce the PV from excursion away from set point. What I mean by that is, you know, if we can address the disturbance before it happens, we can keep ourselves from being impacted by the upset as much. We react to the car going up the hill. Before we go up the hill, then our speed is not going to drop so low as we go up the hill. And it can supplement our feedback control. That means, you know, we still need feedback probably to maintain that speed once we start going up the hill, to maintain the process at its set point. But with feed forward, we can avoid some of those upsets and disturbances, or at least reduce the impact of those disturbances enough so that feedback control is just maybe acting like a trim. And I'll leave this last bullet there, enable optimal control, as a question for you to think about, and I'll come back to it in a minute. If we had really good feed forward control, that I could see the disturbance and react perfectly or respond perfectly to it before it impacted the process. If I could hit the gas pedal just the right amount for the slope of that hill, would I even need feedback control? I'll leave that open for you for a question in your mind while we're going through the rest of this slide. What feed forward cannot do, obviously, is correct for the other errors in your control loop. It cannot correct for bad tuning on your PID feedback control. It cannot correct for a bad sensor, for a bad valve, for the operator putting the loop in manual, you know, all those other things that can go wrong in a loop. It can't fix that. That's not its job. Its job is just to look at a disturbance and make a correction. But it also can't see some types of disturbances or upsets to the process, like process changes, like you know, fouling of a heat exchanger, or a broken piece of equipment, or something like that. It's not going to be able to do anything about that because it can't see that, it can't measure that. And of course, if your loop's not designed properly to begin with, it's not going to be able to help with that. If the valve is too far upstream, that you wind up with a lot of dead time in your control response, if, you know, you have problems like that, obviously you can't do that. And now back again to this question of, can it work completely without PID? You know, what if I didn't have any feedback? Could I still do feed forward control? And the answer is, well, yeah, kind of, but it's not going to be perfect, most likely. And the reason it's not going to be perfect is because there are probably a lot more things other than just the one measured disturbance that are affecting your loop. It's not just that you're going up a hill, it's that the type of pavement changes, or the wind is blowing down the hill or up the hill or to the side or whatever, or you're carrying a heavier load today than you were yesterday, or there's a problem with your engine, or whatever is all the disturbances are happening in your car or in your plant affecting your control loop. The feed forward is only addressing really one of those potential disturbances. So if you really only have one disturbance, maybe it could do it just on its own. But 99.9% of the time, you're always going to be using it in conjunction with feedback trim to take care of all the other things that can be going wrong with that loop. Okay, Vera, let's go to the next slide there.
And so when we kind of expand on that, what makes a good candidate, right? What are some of the kind of applications and things you should look for that make a good candidate for feed forward control? And one is the most important. Your disturbance has to be measurable and available in real time. You have to be able to see the disturbance. You have to have that information available in the DCS, in the PLC. It has to be available to do that kind of calculation. There was a great example of this is there was a parts furnace that I worked on years ago, and basically every now and then the door would open, parts would go in, the door would close. Brilliant, right? And I'm like, yeah, that would be a feed forward application. It's a dream, right? The door is going to open, let's do it. Well, unfortunately, the PID controller was in a different system than that controlled the door, and so the PID controller had no way of knowing when that door was actually going to open or close. So while the idea was brilliant, we had no measurement or sensor available that could tie that PID controller. And so the solution was pretty simple. We moved the PID controller to the PLC where the actual control was taking place, where the doors were opening and closing. We were able to implement a feed forward controller. It worked really, really well, right? But you have to have that disturbance measurable and available. And the disturbance has to do something, right? You don't want to put all this effort in when the disturbance barely has any impact on the process variable. It has to be a worthwhile effort because this is going to take time and energy. And so you got to make sure it's a valuable disturbance, that it actually causes an impact. And so when your disturbance has a significant impact, brilliant. It's going to be a kind of a good application, right? Again, hills are a great example. When you have a steep hill, that's a pretty good impact on your process variable. If you got a tiny little hill, it's not like you're looking forward and saying, oh, I see a grade of 3-inch change on the highway, I need to speed up. Who cares, right? It has to be a significant enough impact. And this third one is really important. The relationship has to be consistent, right? It's got to have some bit of repeatability. So when your correction takes place, it actually does the right thing, right? If a disturbance sometimes causes your temperature to go up and sometimes causes your temperature to go down, your feed forward's not going to work very well because it doesn't know what's actually impacting the process. So you need to make sure it's pretty consistent. You also need to understand that disturbances are going to be somewhat nonlinear with the process, right? If sometimes the disturbance increases the temperature by 20 degrees, sometimes it increases it by 40, there's a certain amount. You want to understand that nonlinearity, and you want to kind of take it for the least amount, because the last thing you want is your disturbance to overcompensate and cause more of a disturbance. You want it to at least take a little bit of the edge off. So when you're thinking about this feed forward impact and its consistent behavior, try to understand it's not going to be perfectly consistent. So you got to kind of understand those dynamics. Now, some are vary, right? Anything that's kind of a mass balance, right? Like steam drums, 3-element control, it's, in equals out, right? It's a very consistent behavior, but things like temperature, that relationship can kind of change sometimes. And again, the feedback response is not good enough. What that means is the PID control isn't going to be good enough, right? And take that parts furnace for an example, right? If you've got a giant oven that's got a lot of thermal mass to it, and you've got all these heaters on it, if I were to crank those heaters up, the temperature is going to be very, very slow to respond, right? It's going to take a lot of time and energy to get that temperature corrected. But if I open a giant door and all that heat rushes out, that is a huge instantaneous disturbance to the system that a PID controller will never be able to overcome solely by itself. I mean, it will eventually, but it's just going to be really, really slow. And so feed forward control in those applications are great because it says, hey, look, the door is going to open. Let's start adding energy now so that when the door opens, I don't lose as much kind of thermal mass in there. So you got to make sure that it's a valuable asset to do this on, right? This is going to take good work, but you do need to make sure it's measurable, that it has a significant impact, that the relationship it's fairly consistent, and that PID is not good enough. So you really want to start talking about some of the high value applications. And George, from kind of your experience, what are some of the high value applications that you've kind of worked on in the past where feed forward has been proven to be valuable?
I think right on the next slide here, when you have processes that have these kind of long, slow thermal responses, that's a good one. I've seen it in waste treatment. When you have a waste treatment plant that might have a process time constant measured in days or at least tens of hours, and you have some upset that comes and hits that waste disturbance plant. You don't want to wait until the bugs start dying and the process starts collapsing before you respond or react to that. You want to get that up front. Reactor controls, as you see on here, boiler controls, blending and ratio controls, distillation columns. Again, these are mostly all things with fairly longish time constants, so at least thermal time constants, or things like in the case of distillation, it could be on the order of several hours of time constant for a distillation column. Heat exchanger is also another thermal type process. These are good. The reason these are all good examples are because they tick many of the bullets that Bob already talked about. They are expensive processes, they consume a lot of energy, so it's going to be worth your while to make some improvement here. They are generally fairly well instrumented, so you can see some of those disturbances that are coming along before they hit you. You can see the change in feed streams, you can see the change in feed temperatures, you can see some of those kind of things ahead of time. So it's going to be worth your while to do it, and you're going to be able to measure that problem, and you'll probably already know if your PID alone is not good enough. So these kind of high value thermal energy consuming or costly operations are good places to go. I agree with you, Bob. It's not so easy as just like, oh gee, I've already got a sensor, let's just go put feed forward in place here, because you have to do some design, some engineering, some documentation, some training operators. I almost think the cost of implementing a feed forward loop is going to be equivalent to the cost of implementing a new PID loop, even though you don't have to buy a valve. It's still going to be about the same cost as putting in a completely new PID loop because of the engineering and documentation and design effort that has to go into doing this properly, especially if you've got to train people that have never worked with feed forward before. So those are some good candidates to think about if you have these in your plants, which you probably have at least one or more of these in your plant to think about.
Yeah, and you know, with these high value applications, you always have to think about too, what are the failure modes? What are the things that can go wrong with feed forward? And if Vera, you want to pop to the next slide, you know, things can go wrong, and you need to make sure that you account for those failure points accordingly. What happens if the disturbance signal disappears out of the DCS, it goes to a bad state or goes to something else, right? You need to make sure that the logic in the DCS doesn't immediately zero out that feed forward because it was added into the math of the PID, and you could end up with a crazy spike in the PID controller. So make sure that you've got that kind of conditioning and failure modes for the measurement sensor. The other is, it's not really a failure mode per se, but you got to be able to measure the different disturbances. And we've talked about a single feed forward. I've worked on feed forward applications where there's 5 or 6 feed forward variables all kind of driving in. And one of the examples I always give is the trash to energy plant, right? And you're burning garbage to make power. And the challenge is garbage is not a consistent BTU, right? It's got a lot of different characteristics. And so you can measure flow, kind of mass of material, moisture content, metal content, recyclable content. They had all these characteristics, and they measured all of those and fed that forward to the furnace and trimmed out the natural gas to basically say, hey, I'm getting a wet slug of garbage into this system. Let's make sure that we are accounting for that. And those kind of built up over time. They didn't start with all of them. They started adding all of these additional disturbances to it as they start to find, hey, here's another major disturbance that can go on here. And so when you start thinking about feed forward, you may not get all of it, but if you can measure another variable, don't think of it as a feed forward can only be one thing. You can add all of these together to kind of create a more sophisticated one, but yeah, it does take more effort, more time, but you get the value out of it.
I think that's a really good point though, Bob, that feed forward doesn't have to be perfect on the first go round, because doing some amount of feed forward is always going to be better than doing none, right? If you get to the bottom of the hill and you stomp on the gas and you stepped on it too soon or too much, well, okay, your regular cruise control and feedback will take care of that once you start going up the hill, right? So you don't need to expect feed forward to be absolutely perfect from the get-go, especially when it comes to the dynamic alignment. Am I doing it at the right time to speed up? If you think about cars going up a hill and then you see like a semi going up a hill, a semi might start stomping on the gas half a mile back before the hill begins, right? Because they know that it's going to take them time to build up. And it doesn't matter if they start a half a mile back or 0.6 of a mile back or 0.7 of a mile, right? It's going to help them more than if they had waited to the bottom of the hill. So that's a good point.
Yeah, that dynamic alignment and the sign and scaling, make sure that your math is correct, right? Make sure it's the correct direction, that you're not hitting the brake before you get to the hill, you're hitting the gas. And I have seen it, right? And it's not a pretty thing. So make sure your signs are right, and a dynamic alignment is really important. Again, if I'm driving a Ferrari, I don't want to start accelerating a mile up the road, but if I'm driving a semi truck, I will need that time. So that dynamic, you want to make sure that correction arrives at the same time as the disturbance. Otherwise, it's really not going to work very well. And so when you're implementing feed forward, there's some challenges and concerns. And if we've got another a survey question here, George, I think you're gonna.
Okay, great. That's good. So as you think about implementing feed forward in your plant, what are some of your reservations at this point in the presentation? What are you thinking about might be some of the challenges? And you can pick as many of these as you see as barriers. Do you think it's going to be too complicated for your staff to maintain it? Do you think it might have a negative impact on the plant? Or maybe that you can't measure the right kind of disturbances? Maybe you've got some feed into your plant that you just don't have a good measure of what's in that feed stream. Might be the cost of implementation, or you think it might be hard for your management and your operations team to accept something new like this. So give us your thoughts here, and we'll take just a minute to go through that. These are all very real. They all happen.
And I would say the last one's always been my, the biggest challenge is just manage it, rejection of change, right? Why are we going to make anything different, right? And we've always done it this way. Why change, right? That's always the biggest obstacle I run across.
Yeah. Yeah, you got two kinds of operators, right? One that says, don't take anything out of my hands, and another one that's happy to say, yeah, okay, if it'll do it, go ahead.
Mm-hmm.
Let the automation do it instead of me. So you kind of have to deal with whoever's the politics of your specific plant there to get these things implemented. Of course, money speaks, right? If you can show the value, the cost of these deviations from set point over time, money talks, and you'll be able to decide if you have the justification to do an implementation or not. And management will always listen to money when money talks. So.
Mm-hmm.
Okay, let's see where we're at here, Vera. Oh, look at that.
Measure, yep. That's
a little of everything.
Yeah, that's a good spread there. Yeah, management and can't measure the right disturbance. That tends to be a lot because you know it, but how do you get the measurement? Is it in the right system? Is it something that you can actually measure in a way that is repeatable, right?
Yeah. One of the biggest disturbances, Bob, in a petrochem plant, this always gets me. One of the biggest disturbances that hits a petrochemical plant, which is an outdoor plant with a lot of thermal processes and so on, is a thunderstorm.
Yeah.
When a thunderstorm comes, the pressure drops, the temperature drops, the rain comes, everything cools down, and that's a huge disturbance to the plant. Can you measure it? Can you measure exactly when it's going to come? That's a tough one.
That's a tough one. And the weather people aren't that great at it. So, I mean, Here in New England, we're either going to get 2 feet of snow or nothing. And you don't know till it starts snowing, which is not very good for feed forward control.
Yeah. Good. All right.
Yeah.
Nice, good spread of responses there.
Yeah. So when we start thinking about designing a feed forward controller, and there's a lot of different methods and stuff like that, but really the idea is you got to start simple. You have a sensor of a disturbance, right? We're measuring something. And what we need to essentially do is understand how does that disturbance impact our process, and then how do we compensate for it? And so we use models, disturbance models and process models, and the ratio of those two become what is known as our feed forward gain. So we take the change of the sensor, run it through the ratio of the disturbance to the process model, and quite frankly, the time constants generally work themselves out. A lot of them you tend to ignore it. It tends to be a gain multiplier and a dead time, right? So you take the disturbance gain over the process gain, that's your feed forward gain, and then you hold on to it for the difference in the dead times, right? So you got to make sure the correction arrives at the right spot. And you basically add the feedback and the feed forward together. Notice here that the feed forward goes into the PID controller. I did not add it after the fact. So I don't take the PID output and then add a feed forward contribution and go to the valve. You need to tell that PID controller that it has feed forward and that there are adjustments, so you don't get like wind up and stuff like that in the controller, because if you don't, the PID controller can ask for 100%. You could add 20% to the feed forward, and now your valve goes to what, 120%? Doesn't really do that. Now you've got wind up in your controller. So all PID controllers, at least modern PLCs, DCSs, they all have the feed forward input slot, pin, whatever you want to call it, into the block. Follow the documentation for your feed forward controller, but it goes into the PID controller, right? So the ratio of the models give you that dynamic alignment. And so usually those are called lead lag blocks or gain blocks and dead time blocks. And you kind of build those kind of series of blocks together, input it into the PID controller as the correction. Make sure your sign is correct. And as George mentioned earlier, It doesn't have to be perfect. Even if you only get half of the disturbance with the feed forward, it's still better than nothing, right? And so you generally want to be conservative versus aggressive with your feed forward, right? If you don't want to overcompensate and floor it and, you know, take your speed way out of whack, because guess what? Your feedback controller is going to say, hey, I'm not at the right set point, and the feedback's going to fight the feed forward. So you want the feed forward to make sure the dynamics are aligned to the process, that the corrections arrive at the same time as the disturbance, and that it doesn't cause more harm than good, right? And so you just want to make sure that you kind of follow the basics there to make sure you understand the dynamics and the process model there. Make sure that the units are correct, right? If you're reading things in, you know, gallons per minute, that you make sure the gains and all that stuff, convert that into percent controller output corrections and so forth. And, you know, there's a lot of kind of nitpicky stuff that you have to do with the different DCSs and PLCs. Generally speaking, there's usually good templates and help guides for how you actually do it. But the key is, how does the disturbance impact the process? How does the controller output impact the process? The ratio of those two models are actually what you use.
Yeah. So just to put this into maybe a simple example here, if we say that we're reaching a hill that's 10 degrees in slope, and I know that a 10-degree slope hill will slow my speed down by 10 miles per hour, let's just say. So my disturbance model essentially is minus 10 miles per hour divided by 10 degrees of slope, or -1. My disturbance model can be something as simple as that, -1, and then maybe with a little dead time or a lead lag on it. That's your disturbance model. And so your feed forward controller takes that -1 and then puts it over your process model. Your process model basically being, when I step on the gas, how quickly will I accelerate, right? So that's basically it, right? That's basically how that works. So pretty simple if we go with just the scalar model there, but also you can add some dynamics. So let's talk about how these pieces fit together a little bit. So on the left-hand side, what do we do to get the feed forward in place? First, we need to make sure we have a sensor. If you don't already have one, you might have to purchase one and install it so that you can measure the disturbance. You can measure your incoming feed disturbance, or your temperature upset, or put a switch on the window or on the door to the furnace so that you know when the disturbance is happening. Then you need to do a model of the disturbance, as we just said, when that disturbance happens, how much is the process affected. Now you can actually use historical data to do that as well. Once you've got your sensor in place and you just monitor your process over a period of time, you'll start to see the impact that it has. And then you can build and configure that feed forward controller. As Bob says, it's going to be different on almost every control system that you have. You've got a PLC, or you've got a DCS, or some type of hybrid controller, or whatever brand you have, it's probably different on each and every one. So again, look for some experience of those who have traveled that road before you, because you can build on that. Now, what about our feedback trim? What's it going to continue to do? Well, it's going to continue to do what it always did. Just kind of keep trimming the process and try to keep us on set point and reject all the other disturbances that come along that are not part of that feed forward thing. Or even if our feed forward model isn't perfect, the feedback will keep doing its thing and keep us at set point. So that's its job. And its job also is to manage all the kind of, let's say, routine accounting of PID control, like keeping in the right mode and handling alarms and notifying the operator and avoiding reset windup, and all of those kind of things that the PID does. It's going to do its thing for the whole combination. So how do we know we've done it right? Right, that's this last box on the right. How do we know we did it right? Well, we'll know we did it right if the models is reasonably describing the process. That is, by implementing the controller, we've been reasonably able to offset that disturbance. Okay. Is the model reasonably good? Was I supposed to step on the gas by 10%, or was I supposed to do it by 1%? Well, you're going to find that out. You're going to know that pretty quickly. So you watch the performance of the overall controller with the feed forward on and with the feed forward off. And again, you'll know pretty quickly by looking at the response to those disturbances. Again, if you look back in your historian, see what the disturbance has been doing, how it has been impacting the process, and then look at it after, you'll be able to see pretty clearly how much of a difference it has made. Also, and we haven't talked too much about dead time, but this is a really important thing that, you know, we want to develop the feed forward controller. We want to invert the disturbance model, essentially, right, when it comes to the time lag and time delay. What that means is, you know, if I know that this thing is going to hit me in 5 seconds, I want to be able to get there in 5 seconds. But what if my PID controller can't respond in 5 seconds? What if it takes 10 seconds to respond? Well, I can't do anything about that, right? If I'm driving the semi and I come around a corner and all of a sudden there's a huge hill in front of me that I didn't expect, oops, there's not much I can do about that. So it is important to pay attention to the dead time response from the disturbance and the dead time response of the controller, just to make sure you've got a realistic expectation of what is possible and what's not possible. We still can't correct for things faster than we can react to them. So,
yeah, we can't time travel yet. Like we've tried, doesn't quite work, right?
Close my eyes, blink, wave my arms, it still doesn't work, right?
Yep. And so when we talk about kind of this designing a feed forward controller, and if we want to flip to the next slide, Vera, you know, kind of just to kind of review what George said, is we want to make sure we understand the impact of and tune the feed forward controller. We want to commission it, and we want to just make sure the PID trim, the PID loop itself is tuned right. And so again, when we think about tuning that feed forward controller, it's really about understanding the correction that the controller output needs to perform. And so if we think about a very simple example like a steam drum, right? How would you tune a feed forward element for a steam drum? Right? It is literally the simplest one in the world, because you think of a steam drum, you're controlling the feed water into the drum, right? And it's going to be in thousands of gallons per hour, for example, right? And so I'm controlling the level by adjusting the feed water flow. The steam demand is the feed forward variable, right? I've got some sort of steam demand that's pulling out 1,000 pounds per hour of steam. Well, that's a pretty easy math balance. If I'm drawing out 1,000 pounds per hour of steam, guess how much feed water I need to put in there? 1,000 pounds per hour of steam water. So if suddenly my demand increases by 1,000 pounds per hour, my feed water flow needs to move immediately with it. And so if you think about the feed forward there, it's literally 1-to-1, right? So as soon as your steam demand increases, increase your feed water flow into the drum. And now they match, and now you've got kind of a feed forward controller. You're not waiting for the drum to get disturbed and try to recover, right? You're just immediately adjusting the in and the out of that steam drum to match, right? And so that feed forward gain would be 1, you know, but if the units are different, you may have to do a little bit of conversion there, right? If it's, you know, liters per minute here and gallons per minute there, right? It's not 1-to-1 anymore, right? You got to make sure you do that. Units matter here, right? So you just got to calculate that feed forward gain. And again, you can look through disturbance data, right? You can see, hey, I got hit by a disturbance, and you know, I got a 10-degree change in my inlet temperature here, which the controller needed to move 20% to correct, right? Well, your feed forward gain is 2. For every 1 degree of temperature, I need 2% of output, right? And so you can look through the data to figure out that feed forward gain, and again, program it into the PID controller so your controller doesn't become saturated or wound up, right? Use those aspects. You commission it, you set it up, you program it. You will probably have to look at some of the dead time compensation, right? You don't want that correction to get there before the disturbance does. So sometimes you got to time your corrections appropriately. And then once you get it done, you make sure that your PID loop is actually tuned, because as George said earlier, feed forward doesn't fix a broken or poorly tuned PID controller, right? It's going to add some kind of additional correction to it. And
you may find that your existing PID tuning was set up because, gee, we need to make it more aggressive because we have these disturbances that come along, and you may be able now to get by a less aggressive PID controller because you've dealt with that major disturbance up front. So
That's right.
Your PID truly becomes kind of a trim on the operation.
That's right. So now you can go back and look at what the control objective is for that PID controller. If I don't have to deal with the crazy disturbance anymore, I may be able to get away with a lot smoother control, which could make your whole process a lot more stable. Now, this is a lot of material that we've covered, and we still have the success story and case study and some more slides. If we want to go to the next one, I do want to say we do have like full training classes on PID tuning and feed forward that cover all different aspects of control. And I know this is a lot of material, and you know, this is spread out. This is a 16-hour class, covers everything from PID, process modeling, derivative, integral, feed forward, cascade, everything over 16 hours. This is kind of our intermediate process control class, the techniques for applied process control. We actually do have an advanced class on top of this that spends, you know, hours on feed forward and cascade, another 16, 18, 20-hour class that's on kind of the advanced regulatory topics. And so we do have a lot of training material. Yes, this is a lot of material to cover in 45 minutes on kind of the basics. And this is us, me and George, talking really fast, right? We run these once a month. These are great ways to kind of get familiar with process control or get reacquainted with some of the techniques and approaches. I think where we're going to kind of wrap up here is on a quick case study here. And if you want to go to the next slide, Vera, I think George is going to kick us off here.
So here we go, and we're going to look at an application here in one of our favorite processes, which is, of course, beer, and a beer canning facility where we had a filler that was having trouble keeping up with changes in the process. So that the brewery had implemented a new type of can here, and the can diameter was a little bit different, and it had an impact on the filling process. So if you're familiar at all with these filling processes, you have hundreds of thousands of bottles or cans, right, rolling through this filling process at once, and trying to keep them all filled at the appropriate level is really critical, because if you overfill it, you're of course giving away product, giving away beer. If you underfill it, then you have to pull those bottles aside, because obviously you can't sell them at underweight or under volume limits. So from the point of view of, is there enough here to be worried about, to think about doing something different like feed forward control? Absolutely yes, because there's a lot of issues and a lot of giveaway and a lot of just kind of culling of these bottles that are underfilled as well. So there's a rework cycle involved in that. It's just a painful, costly part of the process. So the dynamics here were different in the filling process. I won't go too much more into the details of that until we go to the next slide here. So here's a diagram of a filler, you know, all these cans or bottles coming into a filling machine and being fed at the top with the fluid. And now what was happening here is, as the process changed speed, starting up, slowing down, shutting down, the level control was going wonky on filling each one of these individual vessels. Okay, the cans would then wind up being underfilled in some cases, depending on which direction we're going, and overfilled in others. So we had to be sure to make sure to adjust the filling process so that when the line is speeding up or slowing down, we're able to react to that, because and make sure we got to the right level. And Bob, maybe you can add a little bit more to that description so we can get to maintaining the level in each individual can to exactly the right place.
Yeah, and so it really is, you've got these bowls that need to have very, very precise control of level to get those cans and bottles filled appropriately. And if the level deviates during startup and shutdown, you don't get you either get underfills or overfills in the cans. And the challenge that we had is they kind of changed the can geometry a bit and required much tighter tolerances that they weren't able to maintain. So every time you change the line speed from half to full, or did a can stop kind of open close, which is like starting and stopping the line, the level controller just got hit with this huge disturbance that it just had difficulty dealing with, right? It could do it, but not very well, right? It's a purely reactive process, right? If I suddenly increase the speed from 800 to 1600 cans a minute, right, that's going to actually have a fairly significant change on your flow rate, and you have to wait for the level controller to actually recover. And I'm kind of giving the secret away here, but sounds a lot like a steam drum to me, right, for 3-element control. And so if we go to the next slide, the answer was actually pretty simple. It's a feed-forward controller, right? We basically say, hey, look, if we know we've got X number of cans coming off of it, 1600 cans a minute, and we know the volume of the can, right, we can infer the flow, right? Hey, I need 300 barrels per hour for 1600 cans per minute, right? And if I suddenly drop to 825 cans per minute, do a little math, well, I only need 147 barrels per hour, right? And so instead of waiting for the level controller to try to react and figure out what flow is needed, it's just a feed-forward controller. It's a simple mass balance. And so now whenever the line speed changes, the can speed changes, they change from cans to bottles, they change from shorts to talls to whatever it is, you've got a very simple equation that you can use to determine, hey, I know the can rate, right? And I know how much, what my beer flow is, balance those out, and you've got a nice 3-element controller in there. And that actually had a significant impact on the waste associated with this. And you think about the speed of these lines, and I'm sure out of all the participants in here, quite a few of you have seen these, at least on television, how fast they're flying around, 1600 cans a minute. This was 10 or 12 years ago. I think they're up to 2600 cans a minute now. It's mind-boggling. And so when you think about, okay, well, I only produced 1 minute of downtime, well, that's 1600 cans of beer. It's 2000 cans of beer, right? That is, that's bad, right? We don't like wasting beer. So you really, trying to get better and better control is really important. And feed forward actually had a significant value. And if we go to the kind of the final slide here, we'll show you just some data. This is actually data from a canning line with and without the feed forward. And if you look at the top one, I know it's a lot of kind of lines in there. If you look at the kind of light pinkish line that kind of ramps up, that's the line speed, right? So we go from one line speed, we increase it to another. And they didn't go from, boom, boom, like as a step. They did ramp it to try to give the controller at least a little bit of time, but you can still see the level dropped well below the target level. When the level was too low, you ended up getting underfilled cans. If you had underfilled cans and they go into a pasteurizer, it's possible they could pop, they could cause a mess, they actually boil. But if they get caught selling cans that are not full, it's a fine. It's really, really bad. So it's a lot of waste. And so all of that below is waste. A little high is not too bad, right? But the below is what killed them. And with the feed forward controller, what's on the bottom, you can see that the beer flow, which is in that black line, as you started to ramp up, the flow of beer actually followed it perfectly. That feed forward controller brought it up. The one at the top basically was, hey, the PID controller sunk, I slammed the beer open. This actually had a couple of really positive impacts. One is the waste went from 1% to 0.07%, which that's a huge number. It's like $1.8 million a year or some such number. It was a big number. But from a production standpoint, what was really nice is these are not, canning lines don't have a dedicated beer supply. There's a beer loop, and so there's multiple of these canners pulling off the same line. Imagine what that poor beer flow is doing if it goes from 0 to a huge flow, right? You suddenly have now introduced a pressure drop in that line that's now impacting all the other fillers. And so by actually putting a feed forward controller we get better, faster disturbance rejection with less heavy demands on the beer flow. So as George was talking about earlier, now the PID controller doesn't have to be tuned as crazy, as aggressive, because the main disturbance is actually dealt with in a much smoother, much more repeatable fashion, which actually made quite a significant improvement on the process. So that was a lot. I think George could have one more slide to kind of wrap us up.
Time for a beer, Bob.
Tell you what.
Good. Okay, so yeah, just a quick summary of this here today is feed forward. As you've seen, it helps us to get to solve problems before the PV deviates. That's the most important thing. If you take that away from today's webinar, that's the most important thing to think about, is feed forward can help us solve a disturbance before it impacts the process. But it's going to take a bit of effort, right? We have to take a bit of time to model and understand what's going on here. We've got to make sure we've got good measurements. We didn't even talk about, kind of measurement noise and things like that. There's a lot of factors to think about here in implementing our feed forward. So making sure we've got good measurements and a good model will help us get most of the way there with getting the benefits from feed forward. It can be used where we have a measured and predictable response from a known disturbance. That's really what we're after. And it helps to keep our process as a whole far more stable, robust, and in control, and prevent those excursions away from set point. So that is it. And roughly, you now have a rough understanding of what it's going to cost and the implementation to do this. It's about similar to implementing a single PID loop, like I said, even though it doesn't have a valve.
Mm-hmm.
So,
excellent. I think we've got one final just kind of question at the end. If anybody wants some more information, you want to talk a little bit about the tuning software, how you can use Loop Pro to tune feed forward controllers, how we've got services that can help you do some process improvement, information on tuning software. If you want the feed forward checklist that George had just kind of introduced there, we can send you that download link as well to that document, give you a little bit more information. So while that kind of survey is going on, Vera, we've got a couple of minutes for questions. I think we managed to carve out 2 more minutes.
Yeah, so there is lots of questions here. So we are not able to answer all here live, but we definitely are going to be in touch with you to answer the questions after by email or telephone, okay? So let's start, Bob. Feed forward can come from either upstream or downstream on control point in the process. Is that correct?
It can come from anything that impacts your process that is distant to the process. The key here is that you have to see this disturbance coming and have time for the controller output to correct for it. So whether it comes upstream or downstream or as a cycle, you have to have the time. You have to have time to make the correction. So it really has to do with the dead time and kind of the time constant associated with it.
Perfect, thank you. Another one here, the measurement of gas in a car could be an example of feed forward because it informed the operator very much in advance as the gas starts to get finished.
Yeah, I mean, driving a car is mostly as a human, it's mostly a feed forward experience, right? You look out the windshield, you don't look out in the rear view mirror to drive the car, right? So driving the car is mostly a feed forward experience, whether we're talking about the speed or the steering wheel, right? It's mostly a feed forward experience if you want to think of it that way. And then feedback just to kind of trim it and keep it where it needs to be.
Yeah, you could almost think of it as feed forward is you doing everything besides looking at the speedometer, right? Everything else is you being proactive about curve, speed, and everything like that. And a lot of times you don't know exactly where you need to move the gas pedal, but intuitively like, yeah, I need to push it down a little bit to overcome this hill or let up because I'm coming down a hill.
Yeah.
One more here. I have a feed-forward flow to level. It works okay during normal operation, but sometimes operations take the flow in manual to address a process issue, and then the feed-forward to level, it's much too aggressive. It is a good practice to disable feed-forward sometimes, or should I just add a filter or detune? Thanks.
Yeah, this is a question of going back and taking a look at the model, the disturbance model first is where I would start and ask, do we have an accurate disturbance model here? Or is the feedback kind of hiding the fact that our feed-forward model might be wrong?
Yeah, and sometimes looking back at kind of the dynamics that occur when the operator takes it to its own control, that may change how the feed forward actually needs to compensate, because maybe there's less impact or something like that. So
depending on how it's implemented, for sure.
Yeah. So actually, we are on time here. Unfortunately, we have lots of questions more, but as I said, we will be answering all by email or phone call. I thank you all for coming today. Here it's our specialist. If you have any thing to say, or if you want to check out our website, our solutions, to see our training schedule, our webinar schedule, it's all in our website, and you will be always welcome to be in touch with us. Okay, thank you very much, and don't miss our next webinar. It will be very good too.
Excellent.
Thank you, Bob and George. It was a great experience and learning session. Thank you.
Thank you, Vera. Thanks, Bob.
Right.
See you all.
Thanks, George.
Thanks, everyone.
Thanks, everyone.